cuando quieras.
Okay. Welcome, everyone. Today, our speaker at the PIBSA seminar is Tomás Müller Bravo. A couple of weeks ago, I presented the host flows project, and he's a postdoc at ICE, hired to work within this project. Tomás did his bachelor in Universidad de Chile, then his master degree in PUC, in Pontificia Universidad de Chile, and has recently finished his PhD at University of Southampton, supervised by Mark Sullivan. And he, as I said, he started last November here at ICE. So, well, he's gonna talk about Taiwanese supernovae, cosmology, and hopefully near-infrared. I leave you the ground, Tomás. Thank you.
Thanks, Luis. So yeah, as he said, my name is Tomás. I'm going to be working with him. And this talk is about Taiwanese supernova cosmology, and it's more like about like different ways in which we can do cosmology, not just the standard way that that Taiwanese supernova are usually used for doing cosmology. So if you want to know more information about me, here's my webpage down here and my institutional email here. So yeah, I didn't know I was going to be presented, so I prepared like a slide about me. So I guess like Chris already said most about what it was in here, but in case you're wondering, this used to be me like a few years ago. I used to have like long hair, long beard. I shaved the beard like a few weeks back, and recently cut my hair. So now this is the postdoc look. Yeah, so a little bit more about like my research background. I'm interested in all sorts of stellar transients, especially supernovae, but also like tidal disruption events, superluminous supernovae, and like basically like everything that explodes. I'm also interested in cosmology in general and data science, so machine learning, deep learning. I do have some experience about that, and coding. So I code in Python, and this is my GitHub username. And aside from like research and astronomy, I like doing sports. So all sorts of sports, especially like playing football, but also like cycling, swimming, etc. I love music. I love playing the drums. So that's sort of my hobby. And I enjoy traveling different places, like cycling to different cities, towns, etc., and reading. So I'm not talking about reading papers, but reading books and different things. And also like playing video games like PS4 and computer games. Anyway, so now that you have that you know me a little bit more, I'm gonna start with the overview of this talk. So first, I'm gonna start explaining what's the supernova, the different type of supernovae that there are, and especially about like Taiwanese supernovae, which is what I work with, and how we can use them to measure distances. Then I'm going to talk about Piscola. So this is not the drink, this is something else. I'm going to introduce Piscola in a bit, and how we can improve the standardization of these subjects to basically have more precise distance measurements. And the last part of my talk is going to be about flows. So what I'm doing here with Greece, so using the NearInfrared as a new window. So this is my current work, like simulating light within the NearInfrared to test flows. And I'm going to end with like future projects on like what I'm going to be doing these following years. So in a few words, what's a supernova? Well, it's basically a exploding star. So we have a star, explodes, that's a supernova. It's a very simplistic like image of what a supernova is, but it's kind of true. And we have different types of supernovae. On how can we get different supernovae? Well, mainly because we have different progenitors. So we can classify supernovae according to the physics driving the explosions. So if we do that, then we have core collapse supernovae, and as the name suggests, these come from the from stars that their core collapses. So when we talk about core collapse supernovae, the progenitors are in general like massive stars, so above 8 solar masses, more or less. You know that through fusion, stars, they start like fusing like hydrogen, then helium, and so on, moving towards like heavier elements. But when you end up with an iron core, then you can no longer produce energy through fusion. So stars live most of their life in a relatively stable state, because you have energy pushing outward produced by fusion, but you also have the gravitational pull going inward. But at the end of their life, you can no longer produce enough energy through fusion. So then the core collapses and produces these core collapse supernovae. And we also have thermonuclear supernovae, where the progenitors are white dwarf. Basically, these are produced from a thermonuclear runaway. So you have high pressure and a high temperature on the surface of white dwarf that produces this type of supernovae. But we can also classify supernovae according to the spectral features at peak brightness. So if you take a spectrum of a supernova, and then you see, for example, we're looking for the absence or presence of certain elements, especially like hydrogen and helium, but also like silicon, magnesium, etc. And we can classify supernovae like in different types, like type 1a, 1b, 1c, 2. And we have like a whole like zoo, like a supernova zoo, like taxonomy here. So we have type 1a CSM, have type 2b. It's a whole mess in here. Right? Why make it simple when you can make it more complex, right? But this talk, I'm going to focus on type 1a supernova. So type 1a supernovae, if you take a spectrum at peak brightness, you see that there's absence of helium and hydrogen, and you have the presence of silicon. So here on the right, you see like the average spectrum for type 1a supernova. They all look very similar, so it's very easy to identify type 1a supernova. You see the silicon features around here, and some other features like magnesium and some other elements. Now, type 1a supernovae, they are the ones who produce most of the iron elements of in the universe. So, like people who study the chemical evolution of galaxies, and they need to consider supernovae in general, but also like type 1a supernovae. They also produce feedback in galaxies, so they are very important. Now, type 1a supernovae, they are the most commonly observed type of supernova. So they're not the most common intrinsically, but the most commonly observed. And that's basically because they're very bright. And yeah, the progenitor of type 1a supernovae, these are the carbon-oxygen white dwarf in a binary system. So these are in the class of thermonuclear supernovae. And so they're produced in a binary system. So we have like two possible or two main scenarios here. So we have the single degenerate system and the double degenerate system. So the first one is where you have a white dwarf orbiting with let's say like a normal star, like a helium star, like a non-degenerate companion. And the second one is where you have two white dwarfs orbiting around each other, and then they merge. Now, which one is the most likely scenario? This is still under debate. Could be one, could be the other, could be a mixture of both, but we still don't know for sure. And the likelihood of a supernova in general is powered by the decay of nickel. As I said before, type 1a supernovae, they are intrinsically very bright. They have an absolute magnitude in the optical peak around -19. And here on the right, we see an example of this is the closest type 1a supernova to date. So this was a supernova 2011 FE. And you can see it's very bright right there. So the nomenclature that we use for the naming scheme for supernovae is in general like SN or supernova, then the year in which they were discovered, and then a letter that goes with the order in which they were discovered. So the first supernova of the year will have the letter A, then the second one B, and so on. So yeah, this is so I already described what a type 1a supernova is. Now, why do we care about this type of supernova? Well, at least I care because they are standardizable candles, which means that you can use to measure distances. They can be standardized, and you can use it to estimate distances in the universe. So here on the left, we have a like typical P-band light curves of so these are optical light of supernovae. And you see that it rises, then it declines in a given amount of time. And we see that brighter supernovae, they tend to stay bright for longer. The fainter ones, they decline faster, right? So we call this the stretch. So it's kind of like the width in terms of time. So if we correct for this fact, we see that the peak brightness, they all look very similar. So all these different correction standardization, they come from empirical correlation between different light parameters. So as I said before, like peak brightness correlates with this so-called stretch, but also peak brightness correlates with a color, for example, like B minus B, and it even correlates with the host galaxy properties. So, for example, the host galaxy mass or star formation rate or color, whatever parameter you use. The way we estimate these light parameters is by fitting the light curve. So we use light curve fitters and then get these light curve parameters like peak brightness, stretch, and color. And usually, the host galaxy properties are obtained in a separate way. So how do we measure distances? Well, I guess we all know these formula. So we have the distance modulus, which is the logarithm of distance, basically, and that's equal to the the apparent magnitude, so the brightness, the luminosity that we observe minus the absolute magnitude, so the intrinsic luminosity of the supernova, right? So this is very simple. However, this is assuming that they all have the same absolute magnitude, which they don't. But as I said before, we can standardize them, so they all have like a very similar absolute magnitude. So we need to apply this correction to this formula. Now, don't feel overwhelmed, just bear with me a little bit. So here, if we focus on the left, we have the distance modulus. Again, we have the apparent magnitude and the absolute magnitude, same as before. Now, we use the peak brightness usually in the B band as the apparent magnitude, and then we need to apply these corrections. So as before, we have stretch, we have color, and we have some host galaxy property. So the one in green, we use light curve filters to estimate these light curve parameters. So most people use nowadays SALT2, except for this, again, this last one, the host galaxy property. We estimate this in a separate way. And these other parameters here, these are just nuisance parameters. So basically, we have here the distance that you estimate with your supernova. So you can also, from theory, you use your favorite cosmology, let's say flat lambda CDM, and you also have a theoretical estimate of the distance, right? But then if you compare the supernova distance and the theoretical one from your cosmology, you have a chi-square there, so you can minimize that, and you can optimize here these nuisance parameters, but you can also optimize your cosmological parameters, which is what it is usually done. So in here, I'm showing one of the latest results from the dark energy survey. So here we have a beautiful Hubble diagram. So distance modulus on the y-axis versus redshift. So these the dots here, the yellow and red dots, these are distances from the type 1a supernovae, and the different lines are different cosmologies. And the gray line is our best fit cosmology. So again, we have the distances from the supernovae and from your cosmological model, and we have a chi-square here that we reduce, and we optimize the optimal parameters. And here on the right, we have the constraints given by this supernova analysis. So we have omega lambda and omega mater. And we can combine these constraints with, for example, like CMB estimates. and we get the usual like omega matter is about 0.3 and omega lambda is about 0.7. So this is all like very nice, but the issue nowadays is this one here that I'm highlighting. So we see that the statistical and systematic uncertainties, they are quite similar nowadays. And in the future, these systematic uncertainties, they're going to start dominating the error budget. So with the future service like SSD, the statistics they're just going to improve. So this number is going to decrease, but the systematics, no, this number is hard to decrease. So the aim of my PhD project was to how can we decrease this number, the systematics? And sort of like spoiler, one way of doing this is by improving the standardization of type 1a supernovae. So here I am introducing this Coda, which is a Likert filter that I created during my PhD. It is written in Python. It's open source. Now you can pip install it. It's very simple to install and to use. There's documentation here, and it was recently published at the end of last year. So yeah. Now, what's the advantages of using Piscola? So I already mentioned that there's like most people, for example, use SALT2, which is another Likert filter. However, SALT2 is based on templates, so you need to train that filter. Now you have a sample of really well observed type 1a supernovae. You train on those, and then you use the trained Likert filter to fit other new supernovae. However, Piscola is a data-driven, which means that it doesn't rely on templates to fit up the Likers. Now, this is good for analyzing the Likers themselves, because you have access to like the whole correction process, to the output SED. Most Likert filter, they just spit the Likert parameters, and that's all you can use. But with the Piscola, you have access to the whole like Likert SED, so you can explore the supernovae in a much in more in depth. And because it is data-driven, you can fit any wavelength, any band, the UV, the optical, the infrared, compared to SALT2, which only works in the optical bands. And it is also, it's not just like a type 1a supernova Likert filter, but it is generic enough to fit other transients. So this is also like very nice, because you can fit type 2 supernovae, type 1b, 1c. That's very handy, and it's of course well documented, which is very useful. So the how Piscola works, to fit the Likers, it uses Gaussian process. So Piscola fits the Likers in 2D, so the flux as a function of a wavelength on time at the same time. So here on the left we have an observed supernova. We have the GRIZ bands. And you can see here the fits from Piscola using Gaussian process. And I didn't say this before, but for doing cosmology, we want to use the rest frame Likert. Now, in general, the rest frame V-band Likert. So Piscola fits the Likers and then apply all the, for example, the K correction. So this is a relatively high redshift supernovas. We apply K correction, and also dust extinction. We only correct for Milky Way dust. In this case, you get your beautiful rest frame Likert, and you can then estimate your Likert parameters to do cosmology. But as I said before, I wanted to do something else, something like different. So I wanted to improve on the standardization of type 1a supernovae. So then I implemented this new analysis of the Likers. So I decomposed the Likers using non-negative matrix factorization. So if you're not familiar with this, maybe you know PCA, principal component analysis. So you decompose in this case, Likers into a set of eigenvectors and eigenvalues. And this is interesting because here you have these NMF components, and they tell you a little bit about the Liker, right? So this is all data driven. So this is the data telling you, hey, this is important. And here we identified like 3 components. So the first one, the blue one, is basically just the scale of the Likert. And then we have this orange component. It is related to the rise of the light group, so the early part of the light group before the peak. And then the green one, for example, is related to the decline of the light group, so the luminosity after peak brightness in the V band. So this is interesting because you can extract some physics from here, but also related to these components, you have some coefficients, some weights. So these components describe your average type 1a supernova light group in the V band. But for every supernova, like each of these components is going to have a different weight, right? So we can use these weights, these coefficients related to each of these supernovae, and we can compare this with the usual light group parameters. So down here we have peak brightness, stretch, color, this is the host galaxy mass. And we can plot this coefficient against these light group parameters and find correlations between these different components. So as before, as I said before, like this first component, the blue one, is basically just a scale of the light group and correlates very well with the peak brightness. And these two other components, you can see that, for example, like this component in green, they correlate with the stretch. It has to do with the decline of the light group. So the idea here is to, why not, instead of using these standard or classical like light group parameters, we use these coefficients, which come from a data-driven approach instead of an empirical approach. So that was the idea of this paper, and I used these components to measure distances, to correct the light group to standardize type 1 supernovae and measure distances. And what I'm showing here is scattering the distance as a function of redshift between my work, which is in blue, compared to the SALT2 light group filter. So again, we want to reduce the distances, the scattering the distances, and the RMS. You can see that they are very similar. So they are small, like difference of less than 0.01 magnitude. And however, when we are talking about cosmology, like every single like small number counts. So even though like they are very similar, SALT2 is slightly better than my approach here. But this is not bad news. So these are here I'm summarizing our findings. So the first of all, this Coda presents a different and competent alternative light group filter. This is good because, as I said before, like SALT2 work with templates, and now templates, you have some biases because you need to train that template on a sample of type 1 supernovae. But if this sample is biased in a given way, then this bias is going to be then reflected into your fix, right? So this Coda works in different ways, so you can talk from different systematics. So you can study like systematic from SALT2 using this Coda, for example. And these electrical analysis using NMF, well, just with these simple analyses, we already produced like very similar results to other methods like SALT2, which has been around for over a decade. So there's a lot of things that we can implement in this analysis. So I was only using one light group, so the V1 light group, but we can implement like we can include other light groups, so some like color information, and improve this method, right? And also, well, there's a lot of potential in Piscola. So as I said before, you can use it to fit other transit, but like here, when we do cosmology with type 1a supernovae, we usually use the normal type 1a supernovae. But with Piscola, you can also fit other weird-looking type 1a supernovae, and SALT2, for example, only work with the normal ones. So you can even expand on doing cosmology with different like subtypes of type 1a supernovae, for example. But this is like all sorts of like things that we can do in the future. Now moving on to flows, which is what I'm doing here at ICE with UIS. So the idea behind flows is to cosmology with type 1a supernovae, but using the NearInfrared light curves. So if you want to know a little bit more about flows, here's the website. Yeah, so a little bit of context before I start talking about flows. There's this so-called Hubble tension. So if we use type 1a supernovae to measure the Hubble constant, so our local rate of expansion of the universe, we can measure it very precisely to less than 2% uncertainty. This recent paper from Adam Rees. So you get this value here. But you can also measure the Hubble constant, this H0 parameter, using the CMB measurements. So the Planck collaboration has done this in the past. And well, you assume a cosmology, your lambda CDM cosmology, and they are even more precise to less than 1% uncertainties here. Now, the issue, as you can see, is that if you use local measurement from type 1a supernovae and measurement from the early universe from the CMB, you see that you have this difference in number, this difference in H0, and there's a 5 sigma tension here. So this is why this is called the Hubble tension. So from local measurements and early universe measurements, you have a tension here, and this can be due to two main things. So the first one is new physics that we are not taking into consideration here, or maybe unaccounted systematics. And for example, there's some systematics in the way that we standardize type 1a supernovae that we are not taking into consideration here. So the idea behind flows is to study this tension here and basically try to solve it, like trying to understand why we are having this tension here in these measurements. So a little bit of background of type 1a supernovae in the near-infrared. Now, we have known that they are quite standard in the near-infrared for quite a while, like since back in the 80s. So in the optical, they need to be standardized, but in the near-infrared, they seem to be actual standard candles, so no corrections need to be implemented here. And this is in part because the task extension is lessened at this wavelength. So as you may know, task extension affects a lot in the UV, a little bit less in the optical, and a lot less in the infrared wavelength. Well, they can be used to measure distances, and this has been done in the past. And even measure the Hubble constant, and this has also been done in the past. Now with flows, we want to have a slightly different approach. So we want to solve this tension, but from a different point of view, by doing cosmography of the local universe. So basically mapping our local supercluster Laniakea. So by mapping our supercluster, we can measure the growth rate of structure. And you can compare this. So if you take your CMB measurements, you can also, on your cosmology, you can also have estimates of the growth rate of structure. We can compare these values. So again, this is like local measurements versus like early universe measurements, but from a different point of view. But to map the local matter density, we need to measure peculiar velocities, and for that we need to measure distances to the local galaxies. And this is usually done by implementing these two relations, so the fundamental plane and Tully Fisher relations, to measure distances. However, these have a relatively large scatter, so roughly between 20 to 30% scattering distance. So that this is like a huge uncertainties in the distances, right? So what flows wants to do is to use type 1a supernovae in the near-infrared to produce more precise measurements of distance. So here we are comparing cosmic flows. So this is a sample like several thousand galaxies. So from Tully 2016, and you can see that the scatter produced from the near-infrared, like using CSP data, here is much better than using cosmic flows data, right? So this is the idea behind flow. So, well, also the idea is to do some what I call like low budget near-infrared cosmology. So let's say we have like 100 data points in the near-infrared. Do we prefer to have like a few supernovae with really well covered light curves, or we prefer to have like lots of supernovae with just a few data points each? And if we have like few supernovae, but without, sorry, a lot of supernovae, but with a few data points each, then we have a lot of statistics, right? So we can have like 100 supernovae with just one data point each. So that means improving the statistics. And in principle, this is doable because, as I said before, they are very homogeneous in the near-infrared. And we can use Snoopy Lightcurve filter, which is one of the few Lightcurve filters that fits in the near-infrared to fit the Lightcurve. So this is based on templates. As Al2, this is trained on very well measured Taiwanese supernovae. So you have the template and you can measure accurate peak in the near-infrared. At least in principle, that's true in theory. So that's what I'm testing here. And yeah, so you trust me, and you know that this is not all lies. So these are near-infrared Lightcurves, and you can see we have measurements here from like different supernovae, and you see that they all have like very similar Lightcurves in the near-infrared. So they are very homogeneous. So to test the flows, we are using here the Carnegie Supernova Project CSP sample of these are all like very low redshift supernovae. So I think they're all like below 0.1 in redshift, and they have extensive optical to near-infrared photometry. So here we have just two supernovae from this sample. And on the left panels, you see the optical Lightcurves, and on the right, you see the near-infrared. That is what we want to use. So these are like very beautiful Lightcurves, and this is a great sample to test flows. So how do we test flows? Well, we create these simulations in which we take all the optical bands and just a few data points in the near-infrared and see how well we can reconstruct the Lightcurves. And here we have a short video showing you, like for example, like depending on where you take your near-infrared observations, your estimation, your template changes. So you can see how it changes according to the epoch of the near-infrared photometry. So here we have the same, but we have sort of like snapshots all on top of each other. So we can see, for example, if we take our data point around here, that the template does like this, following this sort of like red-ish orange fit. But if you take this yellow point here, you see that the template looks different, right? And we want to focus on the peak brightness, which is what we use to estimate distances. And this is an issue because, well, depending on where you have your near-infrared data, your peak estimate, your peak brightness changes, right? Now, I did this for the several supernovae in the sample. And then I compare my this estimate from the simulations versus our reference sample. So our reference sample is just the CSP sample, but using all the available data, right? So the near-infrared Lightcurves are very well covered. So that's our reference sample. We fit it with Snoopy, and then we take our near-infrared peak magnitude. And then from the simulations, we take our peak, and then we compare this. And that's what I'm showing here. So this residual between the simulations and our reference in peak brightness, and as a function of time with respect to the optical peak. So our findings suggest that if we have so this is simulations with only one near-infrared epoch in the J band in this case. So our findings suggest that if we have one near-infrared epoch around optical peak, then the scatter, as you can see from the plot, gets reduced, and there's pretty much no offset. And the farther away you go from this optical peak, then you get like larger scatter and also larger offsets. But this is not bad because we can correct the Lightcurve for this offset, right? So then what we find here is that flows is actually doable. And the next step is that to actually do flows with real data. And we can implement these corrections to get like accurate estimation of the near-infrared peak in order to have estimation of the distances. So just to finish, so this like part of the future work, well, like during my postdoc here at ICE, is to, well, first, I could improve Piscola. So as I said before, the paper was recently published. So the idea is to get some feedback from the community and see which way I can improve Piscola according to the necessity of the people. Then study Taiwanese supernovae color dependent on host galaxy properties using Piscola. So this is, I didn't talk about this, but this is an ongoing project. And hopefully it's going to be published later this year. And also, as I said before, Piscola can be used to fit other transients. So there's a lot that can be done there. Maybe I don't have time to work on these, but maybe other people can try exploring these other things here. And on the flows side of things, well, I need to publish this paper, these results that I was showing you. So we're working on a draft. Hopefully, it's going to be published in the next few months, showing that flows is feasible. So that's going to be a second paper this year. And then, as I also suggested, is to start flows with the real data. So CTF is producing GNR advanced light curves. So these are optical light curves, and we already have time in different near-infrared facilities. So start producing actual light curves, like real light curves, and start doing flows with the real data. And also another idea is to use Piscola and fit near-infrared light curves. So maybe, as I said before, like near-infrared or Taiwanese supernovae in the near-infrared, they are sort of like actual standard candles, but maybe we can find ways in which we can further improve this standardization, like add some other correction in the near-infrared. But that's also like what we are trying to do here during my postdoc. That's the end of my presentation.
Okay, thank you, Tomás. Is there any question for Tomás from the audience?
No one?
Jordi.
Well, I have the same question that I posed to you a couple of weeks ago. There are several subtypes of supernovae, and we can. How do you take into account this fact? Because the supernovae, they are contaminated. There is a contamination by these subtypes that many of them, they can be less or more luminous than the normal ones. Do you select them before, or how do you do? Because I don't understand such point.
Yeah, good question. I didn't talk about that. So in general, we are trying to use here normal Taiwanese supernovae because we understand them. We know we can, they all behave in a very similar way. So usually, like if you take a spectrum, you can identify these different like subclasses. So we try to remove, for example, the very faint ones. We call them like 91 BG supernovae. We try to remove those, so we don't use those and just try to stick with the normal ones. But usually they are identifiable.
But you have to identify before, and you need the spectrum. To which distance can you go, or to which redshift?
Yeah, so in general, with the near-infrared, we have measurements out to like a redshift of 0.1. Now the spectrum, of course, it depends on the facility that we use, but also like some supernovae, like the subluminous ones, for example, you can identify from the near-infrared light curves. So if you see here, near-infrared light curves, they have like a secondary peak, but the very faint ones, they don't have these secondary peaks. So we can identify this from the at least in this reference sample, we can identify this from the light curves.
Okay, thank you.
Carlos? Thank you, Jordi.
Yeah, hi. I wanted to ask a question that the other day in the talk of Juice, I didn't ask because there was not too much time. It's about this tension. I always wanted to make this question to someone that is an expert. So because the tension, if I understand correctly, what is happening is that we have a function that is the history of the universe in terms of this function, and you try to find this function with different data. On the one hand, you have observations of supernovae, which are kind of nearby universe, right? And on the other hand, you have CMB-based observations, which is really very, very, very far away. But in the end, what we are computing is H0, which is a number that is evaluated right now, right? So I don't understand why people talk about the tension, but it looks like it's not clear which one of the two is the correct one, right? I understand that this is that something has to be wrong in the model, but I mean, for me, given that we have measurements nearby of a quantity that is evaluated nearby, for me, probably it will be something that you need to modify maybe the model so to account for the measurements very far away. I don't know. I mean, maybe I am saying there is something I am missing, but I would like to understand and to know what your opinion.
Yeah, yeah, so this is definitely interesting. But what's happening here between, as you said, we have a local measurement and some sort of like from the early universe that we are extrapolating. So from this CMB, there's a big assumption, and they are assuming that lambda CDM is the right cosmology, right? Right. But this tension, as you said, it could be due to like maybe this model is wrong. And that when I said like new physics, I was talking about like basically changing the model. So this is just my opinion. So we have had like workshops in which there's a lot of people working on theory. So they are trying like different models. So like early dark energy models and all sort of like different models. But when they try to solve this tension in H0, the model breaks somewhere else, right? So there hasn't been like another model that works better than lambda CDM. So just from this, from like listening to other people, like people working on theory, then my point of view is like, okay, then the issue is not with the model, but with the systematics, right? So maybe there's some systematics, and most likely systematics due to the measurement from supernovae. Now I have a plot here that I added. So we don't actually measure H0 directly from supernovae. So they need to be calibrated first. So like in principle, we don't know the absolute magnitude of type 1a supernovae. So we have sort of like a 3-step ladder that I'm showing here. So first, so we calibrate type 1a supernovae with using Cepheids, or at least that's one of the ways we can calibrate them. And Adam Rees uses Cepheids. So you have Cepheids in local galaxies and in our galaxies. So you have this luminosity, period luminosity relation to calibrate Cepheids, but at the same time, you need to calibrate Cepheids using local geometry measurements. So you can use parallax to calibrate local Cepheids, and then you use Cepheids to calibrate type 1a supernovae. And in this whole process, you do have like lots of things that can go wrong, right? And as I said during my talk, for example, type 1a supernovae, the peak brightness also correlates with host galaxy properties. So maybe there are things that we're not considering here. Maybe Cepheids can, there are some systematics that also change according to the galaxy properties. That's the other side of what we are doing. So so flows is part of host flows. So host is kind of like the other side of the coin, in which we are trying to see how, like for example, like host galaxy properties might affect these, or might have introduced some systematics that could be causing H0. So in my opinion, this tension is due to systematics and things that we don't know, and maybe they are related to the host galaxy properties.
Thank you very much.
Thank you, Carlos and Tomás. Any other question? If not, let me add to this answer from Tomás to Carlos that, as Tomás said, this host flows is the whole name of the project, and what Tomás presented it's part B related to near-infrared 1A distances, flows, the flows part. There's the host part where we are using integral field spectroscopy data of around 1,000 objects we have so far. 1A hosts where there are C-fates as well. We have half of the sample from shoes. And the idea is to try to measure stellar population parameters, gas phase parameters at locations of these C-fates and supernovae and see and reduce systematics in the standardization. So that's something that hopefully it will be happening here at ICE by the PhD student, the FPI student that is starting in September. Okay, so is there any other question? Otherwise, we will stop here. You will have some time to prepare to warm your lunch. Okay. So thank you very much. See you next Friday. Thanks. In another pizza seminar. Thank you, Tomás.
Thank you very much.